All right, our topic now is dynamics in cylindrical coordinates. Now, the cylindrical coordinate system is the r hat, theta hat, k hat coordinate system. We'll usually be in the plane and not worry so much about the k hat direction. Just a reminder of the definitions. R is the distance from the origin. Theta is the angle measured in standard position. R hat is in the direction of increasing r. Theta hat is in the direction of increasing theta. Just draw those with a ruler. Now, a reminder that t hat, the tangent direction, is the direction of the object's velocity, and the normal hat, n hat, normal direction is inwards, perpendicular to the tangent direction. We have expressed the velocity previously in cylindrical coordinates and the acceleration as well. Let's do now some dynamics problems. Oh, actually, before we do, one final bit of information. In order to do dynamics, we are often going to need to change between the normal direction, so the nt coordinate system, and the r theta coordinate system. Very helpful in doing that is an angle that goes from the r hat direction to the t hat direction. We use the Greek letter psi for that. Now, psi goes from r hat to t hat. And notice that r and t is in alphabetical order. That's how I always remember it. Now let's just do a little derivation to relate that to the equation of the curved path that the object is following. So here we are, a certain distance r from the origin. And then a little bit later, the object has moved. It's now over here. So there is a slight infinitesimal change in distance. That's dr from the origin. There has also been a change in angle, d theta. And using the arc length formula, we can conclude that this distance right here is r d theta. Now that's very small. Let me blow it up a little bit down here. So here's dr. Here is r d theta. Now, in the infinitesimal limit, these two lines are parallel to each other, and we actually have a 90-degree triangle. Then we can apply the parallel lines theorem, and this angle here, which is psi, will be the same as this angle up here. So down here, this is psi, and therefore so is this. So we can thus conclude, using this right angle triangle, that the tangent of this angle, the radial tangential angle, equals r d theta over dr. Since we usually have the equation of the path, r as a function of theta, we rewrite this as r over dr d theta. So that is its most useful form. So if we ever need to find that angle, the angle between the radial and the tangential direction, this is how we're going to do it. More on that shortly when we get to it in a dynamics problem. Let's look at our first dynamics problem now, just on the next page. So here we've got a ball that's being pushed up a shaft, vertical shaft. So we're looking at this from the side. This is a side view. And the reason what's pushing it up is a rotating arm that's fixed at this black dot, which is the origin. And as it rotates, you can see that the ball will be pushed upwards. Now, we are asked to find the forces acting on the ball. And so we will start with a force diagram. In order to do that, the first thing we'll do is consider our coordinate system. So this black dot will be the origin. So the r hat direction is going to be pointed away from that origin in the direction of increasing r. So there's r hat. Theta hat will be perpendicular to that in the direction of increasing theta. So theta is defined over here as increasing sort of in and I guess that's a clockwise direction. So there is the theta hat unit vector. So that defines our coordinate system. Don't worry about these thetas yet. We'll put them on the diagram later. All right, so there's our coordinate system, and then we consider the forces that act on the ball. Well, it's inside view, and it is being pushed up vertically, so there will be a weight force. we'll assume this is a point object, so we'll draw all the forces acting at that lower contact point with the arm. The arm will exert a force on it, and because it's smooth, the only force that it exerts is a normal force, is therefore perpendicular to the rotating arm. And then you can see that this ball, this 5-pound ball, is resting against the shaft. So there is another normal force there, okay? Again, perpendicular to the surface. Everything is smooth, so there's no friction forces, there's only normal forces. So that is the force diagram, showing the forces acting on that object. Now, we want to write F equals ma equations. That means we need to find r hat and theta hat components of these forces. Now, for gravity, it's going to be very easy because this just looks like a lot like inclined plane components. So it's going to be weight cos theta and weight sine theta. For this normal force here, okay, I did say it was a point object, so maybe I'll put it there. That makes it even easier, doesn't it? Because now we can see alternate interior, zip, zip, zip. This angle is also theta. And so we have a component in the theta direction, in the negative theta direction, and a component in the positive radial direction. So we've got an n cos theta, and we've got an n sine theta. All right, so now we're in a position to write out the force equations. Let me see if I can't make that arrow a little bigger. I guess I can't. Okay, all right, fair enough. So let's write out those equations then. We'll start with the normal direction. So summing forces in the normal direction, or sorry, in the radial direction. Sum of the forces radial. So R means radial. Maybe I'll just write it out. And radial means outwards away from the origin, directly away from the origin. So we've got, first of all, this guy right here, that's normal shaft cos theta. Later I'll write this as NS, S for shaft. And then we've got this component of gravity that is in the negative radial direction. So it's minus weight sine of theta. And that's it. Those are the only two forces acting in the radial direction. That's the R direction. Then we sum forces in the angular direction, which is the theta hat direction. Now, we've got the normal force from the arm, which is purely an angular force. Then we've got this one in the negative theta direction and this one in the negative theta direction. So that's minus normal shaft sine theta minus weight cos theta. And that must equal the mass times the acceleration in the angular direction. Now, we are asked to find the forces when the angle is 30 degrees or pi over 6. So, we know the weight, we know the angle. These equations will be relatively easy to solve once we find the accelerations. Now, we've already previously talked about cylindrical kinematics, and we know that a chart is helpful in this regard, so let us have a look at our chart on the next page. Now, I've sort of redrawn the ball, and that's the blue thing, and then the shaft are these two lines here. I've indicated the distance r away from the origin and the angle theta. Also on the diagram was the fact that this distance was 4 feet. So we can see right away that cos theta is 4 over r. If we solve that for r, it's 4 over cos theta, or it's 4 secant theta. And a little later, we'll put in 30 degrees to see what the instantaneous value of r is. R dot is the time derivative of r. So we have to do the time derivative of 4 secant theta. Okay, calculus 1, the derivative of secant is secant theta tan theta. But because we're doing a time derivative, we have to do the chain rule and multiply this at the end by d theta dt. What is d theta dt? Well, that's theta dot. And it's actually given as a constant in this problem. So to make our life easier, I'm just going to put in 0.05 now, since it is a constant, never changing, secant theta, tan theta, right here. And, well, all right, that's 0.2 secant theta, tan theta. And then a little later, we'll come back and put 30 degrees in there and see what we get for r dot. For r double dot, the second derivative, well, I guess first let's just do the second derivative of theta. That'll just be 0. For r double dot, that's the second time derivative, which means we have to time differentiate this. So clearly we're going to have to use the product rule. So that's 0.2. So let's see. Well, we'll differentiate secant first and leave tan alone. So when you differentiate secant, you get secant theta, tan theta. Okay, we left tan theta alone. And then, of course, we have to multiply all this by d theta dt. That's going to appear in both terms, so I'm just going to factor it out. Then we leave the secant alone, and we differentiate tan, but the derivative of tan is secant squared. And then, because of the chain rule, there's a theta dot term there as well. All right, now theta dot's 0.05, so 0.05 times 0.2 is 0.01, and then we have secant theta tan squared plus secant cubed theta. All right, now I'm going to change color here, and then I'm going to substitute in 30 degrees or pi over 6, and then work out what each of these are. And we need those instantaneous values in order to proceed with calculating the acceleration components AR and A theta. So this, of course, is the radial acceleration. So it's r double dot 0.0192 minus r times theta dot squared. And so we need to compute that. It's 0.00765. These will be units of feet per second squared. This is the acceleration in the angular direction. Theta double dot 0, so that first term just disappears. It's 2 times 0.13 repeating times 0.05. So that just works out to be 0.013 repeating feet per second squared. So that finishes the kinematics, and now we can just substitute into our dynamics. Changing the slide. Here's the equations rewritten for us. I substituted in the fact that the weight was 5. Remember, in the imperial system of units, we need to divide that weight in pounds by the gravitational field strength, which in units of feet per second squared is 32.2. So we substitute in, so normal shaft, there it happened finally, not going to write out shaft, 30 degrees minus 5, that's the weight, sine 30 is the mass, times the radial acceleration, which was 0.00, looking back, 765. So we shall solve for the normal force from the shaft and get 2.888 pounds of force. Oh, silly me, it was right here. Oh, why did I do that? 888 pounds. So sorry. There's the space. And then we scroll down a bit further, and then we can substitute in to find the normal arm force. Mass again is 5 over 32.2. And the theta acceleration that we calculated is 0.013 repeating. So we solve for the normal force from the arm, and we get 5.776 So there you have our first cylindrical dynamics problem. Pretty much a standard force problem. Draw the force diagram, write force equations, do any kinematics, and you're done. Let's try another one together. So again, these problems, there's always a lot of, like rotating rods and things like that. So once again, that's what we have here. So it's a little sliding thing here, this little circle. It's traveling along this sort of curved groove, and we have the equation for that groove. That's r as a function of theta. These are, of course, still just the x and y axes, but this distance here is r, and this angle here is theta. And we'll indicate our coordinate system here. So r hat is in the direction of increasing r. Theta hat is in the direction of increasing theta. It will be useful for us to remember that tangent is tangent to the curve in the direction the particle is moving, and n hat is perpendicular to that and inwards. Now, let us consider the force diagram. Well, I've got it drawn again down here, just to make things a little cleaner, I suppose, because we had our coordinate system up there, and now, whoops, don't move that. It's supposed to stay there. Let's draw the forces on here now using this one. That's what I remember. All right, so this is in top view. So the gravitational force is into the page, presumably, and balanced by some sort of normal force. This must be sort of taking place on a tabletop. So the weight force will not enter into our analysis. So the only two forces acting on the ball are going to be a normal force, again, from this rotating arm or rod. That's going to be in the theta hat direction. And then where the ball touches this curve, there'll be another normal force. Okay? Now, that normal force is going to be in the n hat direction. Just rotate it a tiny bit there to make it look like that. There we go, that looks a little better. Okay, and so we are going to want to, okay, don't worry about that yet. Sorry. We're going to want to break these forces down into components. Now, the copy, bring it down here. For the normal force from the rod, it's easy because it's purely in the theta hat direction. But the normal force from the track or from the groove, you can see, it's in the n hat direction. We will have to resolve that into components in r hat and theta hat. Okay, so in order to do that, we need to know something about the angle at which this lies. Well, this is where our radial tangential angle is going to be useful. Oh, it's not letting me cut and paste that. Oh, how sad. I'll have to draw it again. So let's quickly draw where the tangent direction is here. So tangent to the curve looks about like that. Okay? And as we defined at the beginning of the presentation, psi is the angle from the radial direction to the tangential direction. And there's a way that we can find it. Now, the reason that'll be useful is, well, r and theta are perpendicular, so this angle here will be 90 minus psi. T hat and n hat are perpendicular, so that means this angle right here is psi. Now, you could use that one to find the components of this normal groove force, but I'm going to choose to draw the components over here using this triangle. And then I'm just going to use alternate interior to say that this angle up here must be psi. So if I can find the psi angle, then I can just work my way through the triangles, and I can find the angle in this triangle that I need to find components. Well, as per our derivation, we recall, I'll write it right here. Well, first of all, I'll remind us that psi goes from r hat to t hat in alphabetical order. And I'll remind us, maybe down here, that tan psi is r divided by dr d theta. Now, what do we know about r? Well, scrolling back up, r is 1 plus 2 theta. And so dr d theta, we're doing the theta derivative of 1 plus 2 theta. That is just 2. So this is tan psi. Now, we are asked to do our analysis, if you read the question, find the force exerted by the rod when theta is pi over 4. Now we have to use radians here because anytime you have an angle that's not inside a sine or cosine function, if it's out on its own and you're doing a calculation with it, then you have to use radian measure. So we are going to, in order to find our psi angle, do the arctangent, the inverse tangent of 1 plus 2 theta over 2 at theta is pi over 4. So this means, I hope this is on the screen, so we're going to do twice theta, so we'll do, pi divided by 4, it's just a number, then we multiply that by 2, we add 1, find what that is, then we divide that by 2, and now we do the inverse tangent of that, and I get 52.12 degrees. Now it's kind of lost in that silly mark that I can't get rid of, unfortunately. But there you have it, 52.1 degrees. Now you noted that I chose to answer this in degrees, right? Because when I'm doing an arctangent, I can answer that in degrees or radians. But when I did this calculation, it had to be radians. There, I didn't have a choice. Let's proceed to write out our force equations then, now that we know that psi angle. So sum of the forces in the r hat radial direction, well, there's only one, this guy right here. It's in the negative radial direction. It's normal groove sine of psi. And that's got to equal the mass times the radial acceleration. Sum of the forces in the angular direction, well, there's two. We've got normal rod, positive, I guess to be consistent, I should call that NR for normal rod. And then we've also got normal groove cosine psi in the positive angular direction. So we had to do a little work to find out what that psi angle is, but the dynamics was fairly straightforward. And the kinematics is also much more forgiving in this problem than it was in the previous. There is somewhat of a complication, though. So we know that r was 1 plus 2 theta. That was given. So we can do r dot. It's the time derivative of 1 plus 2 theta. That's just going to be twice theta dot. Now, theta dot, sorry, there is no complication in this problem. It's a constant. So twice theta dot is just 0.4, not changing, so r double dot is 0, theta double dot is 0, and we quickly wind our way through the kinematics. Here's r, the radial acceleration, it's 0 minus, I forgot to change the green color. We work out the value here at pi over 4. There we are. I think we're in meter units here. Nope, we're not. We're in foot units, good old imperial units. 2.571 feet. Okay, so now back to the calculation of acceleration, radial acceleration. So 2.571 times 0.2 squared. So that works out to minus 0.1028. And this will be the acceleration in the angular direction. Put the double dot 0. It's just twice r dot theta dot. It's positive 0.16. So we substitute in to calculate our normal forces. That was a 1.2 pound slider. 0.0485 pounds. Scrolling down a bit. And there you have it, a couple of cylindrical dynamics problems.